just to the introduction, just 1 minute, and then we start.
So here we are.
Okay. Just to the introduction, Alberto, and then I'll let you.
Okay,
so,
thank you.
So thanks to all of you to be there for this session of the AIDA AI Excellence Lecture Series. So as usual, you will have access to the PDF and the video on the website of AIDA. You have also the program for the next sessions of lectures. I will be back on that at the end of the lecture. But today I'm pretty happy to introduce Professor Alberto del Bimbo, who is full professor at the Department of Information Engineering of University of Florence. And he's well known on several stuff, and including the social interaction. And today he will present us some interesting works about social interaction trajectory prediction with memory augmented networks. And as usual, prepare your questions and ask questions through chat or at the end of the lecture. So thanks, Alberto, for being there and for giving the lecture. Thanks. The floor is
Thank you, Mohammed, for the introduction, and welcome everybody for this lecture this afternoon. So, as Mohammed has introduced before, this talk will be about trajectory prediction, and particularly about trajectory prediction in a social environment, in a context where other people may exist, and therefore trajectories of individuals have to take into account trajectories of other people coming around. So we will discuss the problem, and then we also discuss some recent achievements of ours where we use the special type of neural networks that are memory augmented networks. In other words, networks with memory that can be trained end to end. So let's start with a short introduction of the problem. This is Naples in a summertime day. You see the situation we want to emulate with our machines. We want, for example, a robot to be in this crowd, avoiding to meet other people, avoiding to create disorders. So in order to be that, we have to make machine understand how people move. And typically, people have a stochastic behavior. There are unwritten rules, social rules that lead people movements. There is common sense in their movement. And moreover, many people walk in groups. So a system should observe behavior of near people and possibly anticipate what will happen in the very next future. So this is our goal, make machine emulating what humans typically do. In other words, predict human trajectories by modeling social interactions. So let's say why this is important. Well, mainly we believe this is important for autonomous vehicles. More in general, with social robots. It's also important for surveillance systems. Let's say predicting trajectories basically is important for having safety decision making, and also to have safe control processes. Let's define the problem a little bit formally. The approach we have in the literature, and we follow, treat trajectories as sequences of top view spatial coordinates in a 2D plane. So the reference is fixed and independent from the agent. We have a number n in general of people, each of which is moving, and we have a past, the blue dotted line and dashed line, and we have future, the red one. Typically, we want to estimate more than one future. We want a number of futures. So the problem is inherently multimodal. Of course, each of these future trajectories has a probability associated with it. The issue of this problem is modeling both the temporal and the spatial aspects of the problem. The temporal, that has to do with the time from the beginning to the present, and from the present to the future, and the spatial relationships between the people in the context. So let's review a little bit the literature. The literature is very large, and here I just sampled a few papers that gives an idea on how both time and space have been modeled so far. One of the very early works has been Social GAN. This paper is interesting because they use an LSTM memory network to encode the temporal aspects of the problem. So time instant are given one after the other to the LSTM machine, and the LSTM recurrent network is used for each moving agent to encode the motion. As to the spatial information, they use a simple pooling mechanism. I will show it in detail in a moment. So first we have modeling of the temporal information, and then this temporal information of the many different agents is aggregated using a pooling mechanism. After the pooling mechanism, the spatial information is associated to the individual information, to the individual state, and then, a distribution of possible trajectories is generated, which is sampled by a decoder. So the decoder has the goal to generate future trajectories. All the system is trained using GAN. So this is one of the way in which trajectories are generated. The other is using variational autoencoders. More than one trajectory is generated, and this is made using the variety loss that minimizes a number of k possible trajectories. We talked about the pooling mechanism. This picture shortly tells about this mechanism. It is quite simple and is used to take into account spatial information. So basically, given one agent, it builds a grid around the agent. Look at the red agent in the picture and consider the distances between this agent and the other agents over the grid. These distances are encoded, and then they are concatenated. Their encoding is concatenated with the individual states, hidden states of the people you see here in the pooling module. Then simply a max pooling is made over the grid. The max pooling, as you know, is just resumed in this part of the slide. So once we have this information, this compact information, P1, this P1 is added, concatenated to the individual state of the red agent, and then also to the distribution of trajectories and the decoder given to the decoder for trajectory sampling. So what are the drawbacks of this approach? One drawback is the memory that is used. We know that recurrent architectures like LSTM are parameter inefficient and also expensive for training. So basically, we collect all the history information in a global descriptor, which is the LSTM state. The other drawback is also on the way in which spatial information is managed. Because such aggregation of max pooling is not, let's say, well suited to model meaningfully the interaction between people. Finally, also the GAN generation is something that can be debatable. Particularly, it doesn't consider the structure of the environment. So it could happen that trajectories that are generated are not feasible because of the physical structure of the environment. So based on this, on some of these considerations, another approach and others similar follow graph-based modeling of spatial interaction between people. In other words, people in the scene are modeled with a graph, with a spatial graph that takes into account the relative locations of the agent at a certain time instant. So we have a graph for each scene, and given a temporal interval, we have T frames with T different graphs. So we have, in other words, the spatio-temporal graph that represents what happens, the spatial relationships of people in T frames. This spatio-temporal graph is passed through to a graph convolutional neural network that creates the embedding of space and time together. Then after that, we have a time extrapolator that has the goal to predict future trajectories using just convolution operators. So this system is interesting because on the one hand, provides a more direct modeling of spatial interactions using graphs. And on the other, because doesn't use LSTM network, but just a convolutional neural network. So in other words, it's a stateless system. So this being a stateless system provides high gain in parameter efficiency, of course. And on the other hand, the graph modeling provides the possibility of weighting differently people. In other words, people close to the, just to omit another, people close to the agent are weighted more than people far away from him or her. There are a few drawbacks with that. And basically the drawbacks are due to the fact that graph structures are fixed size structure. So only this model only models the interactions of people or agents that are spatially close. So beyond certain limits, their influence on the trajectory is ignored. To avoid that, other papers had a different approach, and the approach was having two steps. One step is estimating the goal. In other words, where is the final destination of the agent? And the second step is, once you have the goal, predict the realistic trajectories to that goal. This paper's goal gun is one of the first that followed this approach. It used memory networks like LSTM to encode motion of the agent's past trajectory. And there is a module that is the goal module that predicts the most likely target position of the agent. And doing that, it considers the motion of the agent and the layout of the scene. You see that in the figure here, the layout and the motion, and predicts the goal. The goal plus the motion is input to a routing module that has the goal to estimate the set of plausible trajectories and then route the person, the agent, towards the goal. To generate multiple trajectories, the GAN is used to train the generator. One good point of this approach is that trajectories here are realistic. Realistic because we take into account the context in order to generate trajectories. So the drawback is that, at least in these papers, the author didn't take into account the other agents. So neglecting the other agent trajectories could result in wrong trajectories, future trajectories to be estimated. Another final category of papers that have been discussed in the literature used, of course, the transformer network. We have seen in the previous examples that one of the issues is having some form of attention. The form of attention is, for example, given in the pooling-based approach, where in the graph-based, they consider proximity as a sign of attention. The closer you are, the more attention you get. Also, in the goal-based approach, the attention was given by the goal, the final destination of the trajectory estimated. Well, the approach using transformer has inherently the attention function in the transformer module. So as you can see from this slide, in this paper, the authors provide two kinds of attentions. One attention for time with the temporal transformer that takes into account the sequence and try to understand where are the salient points in the sequence, and the spatial transformer that takes into account an adjacency matrix plus the output of the temporal transformer. So these two attentions are then combined by the cross-attention module, where each of these modules takes into account both the time encoding of the agent trajectory and the spatial information related to its neighbor, and the vice versa, the cross-attention takes into account the spatial encoding and combines with the output of the temporal encoding. Of course, the mechanism is the same as usual in transformers. You have the query and the key and value, and these are combined differently in the two transformers. So what are the pros and cons? Of course, the transformer is more powerful than LSTM in modeling temporal dependencies. This is basically due to the self-attention mechanism. It avoids pooling as in the previous approaches. It's also powerful for the spatial interaction. The self-attention mechanism of the transformer can be a valid substitute of the social pooling of the other approaches. In addition, the feed-forward nature of transformers makes them efficient on the hardware machines. Nevertheless, there are some limits. One limit is that due to its architecture, transformer cannot process hierarchical inputs or perform algorithmic tasks. We will see what we mean with algorithmic tasks in the few slides in the following. Moreover, the depth of sublayers of the transformer limits also the number of transformations that we need, that we may have. So if we have an internal state that is continuously updated, this could be limited by the depth of the transformer sublayers. All the input is managed in parallel. That means that we lose the high-level representations as we may have, for example, in CNN. So high-level representation of the past are not exploited to compute the current representation. But probably the most critical issue with transformer in this kind of problem is that due to its nature, the transformer takes into account both essential and non-essential information. It just gives attention, and will give, of course, hopefully, more attention to the essential and less attention to the non-essential information. But both are considered. So there is a waste of information that is in transformers. So based on these considerations, we believe that an alternative option is the usage of a working memory. A working memory could be used to store relevant information that is relevant to take decision. So to steer the trajectory in the right direction. So having a memory allows to keep track of the very relevant elements that have happened in the history. And also avoids to blend all this information in a single state, as it happens in LSTM. So the model we are looking at is the Memory Augmented Neural Network model. This is a model where we have a memory which is trainable and a controller that is allowed to write and read from the memory items of information. So in the memory, there are a number of independent states, individually addressable. And what state is read or write or written is decided by the controller. So we can think the controller as a CPU and the external memory as a RAM. The difference is that we have all of this is trainable. So if we want to compare this model with the LSTM model, the classical memory network model, I tried to resume the differences in this slide. In the memory network model, the classical memory network, you have inputs fed to the machine one by one. So there is only one chance to look at an input symbol. The history is stored in the state of the machine. With the memory augmented network model, all the symbols are put in the memory. So each symbol is individually addressable and is the controller that decides which of the symbols is taken off the memory, and also which symbol is read next. So this model was, the idea of this model is credited to Alex Graves and his mates in 2014. And they proposed the so-called neural Turing machine, which is a memory augmented neural network that learns to read and write individual items of information from an external memory. And the system is made by a network controller, that is the interface between the input and the memory, that activates read and write heads that performs respectively read and write over the memory bank, which is just an array of vectors. What was the problem? The problem was that reading and writing from a memory typically requires either an argmax or select operation. And these operations are not differentiable. In order to have a differentiable reading and writing, they use blurry operation. In other words, they interact with all the elements in the memory according to an attention weight. They interact to a greater or lesser degree with all the elements in the memory. So the degree of blurriness that we have to address the elements of the memory is given by a form of attention mechanism. And the attention mechanism is what makes a read and write operation to interact with the memory, so that only the items that are under high attention focus are provided in the output, or in other words, influence the outputs. So making, in summary, a comparison between this model and the LSTM and MATES models, we can say that memory in the LSTM is a single hidden state vector. All the information, temporal information, is stored in the state. In the memory augmented neural network model, we have an external memory matrix. So there are a number of items that are stored there, individually addressable. So in the LSTM, due to the presence of the internal state, the memory is addressable as a whole. So all the past information is encoded in the state vector. In the memory augmented neural network model, the memory is element-wise addressable. So we use attention to select the individual items that are of interest for the task. In the LSTM, state-to-state transition is unstructured. In the memory augmented neural networks, transition from one state to another are obtained using read and write. So this makes it possible to generalize to very long sequences. You can take all the items in the memory, all the items of information that are important through time, and also to learn algorithmic tasks. So in other words, select what information is needed from time to time. Another important issue is that LSTM, the number of parameters, is tied to the size of the internal state. Here, the number of parameters is not tied to the size of the memory. Finally, due to these features, the memory augmented neural networks have, our problem, have the ability to track very long sequences, process hierarchical inputs, and maintaining an internal state for a long time. We have included this model in a system that we have called SMIMO, that stands for Social Memory for Trajectory Forecasting. This is an end-to-end differentiable model and is based on the memory augmented neural network as an essential part of its architecture. You see here a very high-level overview of the system, where you can see two people and their past trajectories, red and blue. And you see the system that has an encoder, and then you may recognize the memory augmented network structure with a controller that allows to read and write from an external memory. And finally, the output of the memory is given to a decoder that has the task to perform a future prediction. Multiple trajectories are obtained using the variety loss. So let's look in more detail this architecture. So, and let's see the module that are that play and the role they play for each agent in the context. So the very first module is a motion encoder. It's a motion encoder that takes into account displacement of positions of the individual agent I. Of course, we create some embedding, And the embedding is given to a motion encoder, which in this case is just a GRU. So it's a recurrent network. This is the egocentric stream, nothing new with respect to what we have seen before. So we encode the history of motion of the individual. Then we have the most interesting part, which is the social encoder. The social encoder takes into account the position of the agent. So for agent I, the position is xi. And creates an encoding, and the encoding is given in input to the memory augmented network model that builds the social encoder. The memory augmented network shares the memory with the other agents. So you see that out of the dashed line, because it's shared between several agents. So each agent writes and reads from this memory. So this memory contains information about the positions of the agents in the context. The output of the social encoder, and we will see in a moment how this output is provided, is the social stream. In other words, is the information about what happens in the neighborhood of agent I. So this is concatenated to the motion of the agent I. And the two information are given to the trajectory decoder, which is in turn a recurrent network. This is decoded and finally provides the future trajectory. As we told, the social encoder is the agent social encoder. So we have as many social encoders as many are the agents in the context. Each of them has a read head and write head to read and write from a memory according to the memory augmented network model. So they are trained to read and write in the memory which is shared. So all the agents share the same external memory. So let's give a look quickly on how reading from this memory is performed. On the very left of the slide, we have the social encoder. The social encoder has a controller that is a GRU, so is a recurrent network. It provides a feature that inputs to the read head to perform addressing in the memory. So given the input, this feature looks in the memory similar items. Similarity is made according to cosine similarity. It also provides a strength, so let's say a form of attention on these shared memory items. So the attention plus the weights, basically the items in the memory. So each item of the memory has a different weight. And these weighted items are summed together to provide the output, the sigma output. The sigma out, therefore, is something that condenses the history of the agent, because we gave in input its position to a recurrent network. So in some sense, we have information about its past. And also takes into account similar situations. So in other words, situations that are given by other agents. In fact, the memory is shared between all the agents, so contains items not only of the I agent, but also of the other agents. So this sigma condenses the history of the I agent, but also its neighborhood, taking into account what is its direction, but also where are the trajectories of the people, the other people in the surroundings. This is some way schematized by this picture on the right side of the slide. We have more than one read head to provide multiple possible social features. And this multiplicity of social features is used to then make a pooling and taking the most interesting between them and feeding it back on the next time instant. So in the input of the controller, we give the current position and also the information about the neighborhood at the previous step. We told that these memory augmented networks are also allowed to perform writing, not only reading. And writing is important because in this way we avoid the overflow of the memory. And writing is just made following the same mechanism. The controller leads the write head to perform addressing in the memory and produces an erase vector to delete some part of the memory that are not anymore interesting and add a new vector to replace the previous one. So this is, let's say, a way in which only relevant information is maintained in the memory. So the overall system is trained to keep in the memory only the relevant information and discard, erase the information that is not relevant anymore, differently from the transformer, and also reading then the most important information for the trajectory prediction. So here you have some results. This is the ATH UCI, where we have 3 predictions for each element, 1, 2, 3, you have seen them. And this is another example where we have a group of people with 3 predictions. Again, and you see that the system is able both to capture also the group movements and understand very well how to predict trajectories that avoid clashing. Let's skip this and just let's go to a few numbers. You see that the performance of the system is quite good on these data sets. And let's say very, very close to the trajectron system that is one of the state of the art. But we believe that you can also see that when estimating k equal 5 number of trajectories or k equal 20, the SMIMO system has very strong performance, for example, on the SDD dataset. These datasets, you know, are quite saturated, let's say, and because situations depicted there are realistic, because they are real world datasets, but don't take into account an important aspect, that is the possibility of having decisions that are some way similar to algorithms. So we create a new dataset that is a synthetic social agents dataset, where we have from 3 to 10 agents. The dataset is quite simple because it's a circumference, and you have agents that must go towards the center of the circumference with a constant speed, but speeds are different. So when two agents get close, the rule is that the agent with greater speed passes and the other must stop. And so in other words, these are what happens. This is a simple scenario, the ground truth and this MIMO system. And you can appreciate that, at least in this example, these are followed quite well. An interesting aspect on this data set that is due to the read-write mechanism that we talked before is, for example, looking at the agent speeds. For example, here, the 4 agents we have seen in the example before, we compare the speed as given by this MIMO system and the speed as given by the LSTM. The blue is the LSTM, the GRU indeed, and the red is this MIMO system, and the green is the ground truth. You see that there are 2 agents that don't stop, those with higher speed, and we see that agent 0 and agent 1 are, almost, this MIMO almost predicts the ground truth differently from LSTM. For agent 2 and agent 3, the task is more difficult because these agents have to stop at some time in their path. And we see that the ground truth is exactly followed by the MIMO system differently from what happens with the GRU. Of course, we have scaled to many different scenarios. Here an example with the 7 agents. So the problem must be much more complicated as it may appear to a first glance. On this dataset, we compared with the other systems just to check how much these systems could be able to solve algorithmic tasks like this one. And you can see the strong difference when this kind of reasoning is requested to the machine, and the very good performance of MIMO. And in the ablation study that you see in the bottom side of the slide, you also see the relevance of the memory. The learnable memory that we use, comparing in the case in which we have a full reset of the memory, or filling the memory with zeros, or just reading random, or just taking states by pooling. The ADA and the FDA and Kendall are respectively the final displacement error, the error at the end of the trajectory, the average displacement error on the average along the trajectory, or the order of the agents when passing through the center, the Kendall measure. So the very final part of my talk, I want to give you also an idea that using memory augmented networks also provides explainability. Just because you have individual items of information that are stored in the memory, so you are able to understand which information is relevant to your task. So to make it clear, just an example with 4 agents in the same SSA dataset that we have built, and just a 60-second example with the 4 agents with the 4 different speeds. So these are the 4 agents, and this is on the right side how the memory is modified during the example. You see the agent controllers on the very right, their focus, and the memory that has been partitioned in 4 different slots for each one for its respective agent, agent A, B, C, D. So the stronger the color, the stronger the attention of the agent, the controller, over one part of the memory, and therefore over one of the other agents. So let's look inside this example more in depth. So let's look what happens from 0 to 31. From 0 to 31, at time 31, we are in this position. So agent C has been faster than the other agents, so it's closer to the center. Among the others, agent D is faster than agent A and B. Agent A is slightly faster than B, but being close to D has to stop. So with respect to B, at time 31, it is late. So let's give a look how we can read this fact in the memory. So the behavior of B is that he gives attention to A, because A, was faster, so should have been ahead of B, but because of D, it stopped. So now is close to B, and B provides some attention to A in order to define its future behavior. Differently, we see that D, the main focus of D, is on agent C, that is very close to him and a little bit ahead. Finally, agent A looks at agent D, and agent C, in its turn, looks on agent D. If we go a little bit ahead from frame 31 to frame 42, you see that 2 of the agents, the fastest ones, have passed at the center. So if we now look at what happens in the memory, we see that, agents C and D read empty space. That means they don't care anymore about the others. What happens to agent A? Agent A was faster than agent B, but had to stop. We have seen it before. So now it's very close to B, and is faster. If we look at the controller of agent B, we see that B gives some focus on agent A. So let's now go ahead. All the agents have passed, and if we look at what happens in memory, we can see that all the agents read empty space. That means they don't care anymore each other. So in conclusion, we hope we have given you, some ideas on how to exploit these memory augmented networks. And particularly, we have applied these networks for trajectory predictions. And we have shown that we may have several interesting results from these networks. Particularly, we can provide multimodality, but more important, we can maintain internal states indefinitely in the time, because we can store whatever information is needed that we want. We provide filtering of information, only information that is relevant. Instances of information that are relevant are stored, so irrelevant information is not stored. And even very important, especially for autonomous vehicles, is explainability. So we can understand why a memory controller makes some decision and what drives this decision. These are a few references, very few indeed, because many others exist. And finally, thank you for your attention.
Thank
Glad
you.
if you have questions.
Thank you, Alberto. Any question? You could ever raise your hand or ask a question through the chat. Yes, there is a question from Barating. Are you going
to benchmark for all the methods? Not personally. If the researchers in my group will spend very much time, I will be glad to do it.
Any other question? Again, you could ever ask for the chat or yes. It is a question from Nasri. Do you see that in chat?
Priority to the agents. We don't give priority explicitly to the agents. When we train the network, using the variety loss. So we train the controller to learn which are the rules of behavior in a crowded environment. So in the very end, we don't give explicit priorities. We just give implicitly through the training good rules of behavior. There are no explicit priorities. The controller, as you have seen, the goal of the controller is to look for similar items in the memory, similar to the input, and to assign, this is the very important point, to these items weights that are attention weights. So it's a mechanism of attention which is different from the one you have in transformer, where you match one element with all the others. So you have self-attention. Here is different because the controller is learned to provide attention based on the goal of your task. So has to learn something like an algorithm. And of course, we don't give the algorithm in an explicit way in this problem, but we just try to adapt future trajectories to the ground truth.
Okay, great. Thanks. There's another question from Anna.
Did you try to use the methods to predict more complex behavior like in a cooperative competitive game? I believe that in principle, this kind of networks are very well suited for that. I believe that. We didn't try.
It's another question. Did you try to use it in a corridor and to make comparison?
To make a comparison with the real. What do you mean with a corridor? I don't understand.
If you want to talk here, you could talk. I mean,
I'll wait. Oh, I don't know. I don't know. I didn't consider this option yet. Anyway, thank you for the suggestion.
Any other question?
To simulate a crowd in a corridor. Yeah. Well, we could try to do. In this case, we have to increase our sample data set with this case. Could be interesting because in this case we have also spatial constraints, more realistic spatial constraints. Thank you.
Okay, you have another question from Vlad.
Static attractors. I think I'm not able to answer, but you mean that if we can, improve the system in a goal-like way, in other words, taking the best from the goal-based approaches that we have discussed from the literature. I don't know. Indeed, don't know. Don't know. I should think a little bit of that. A goal could be something that steers the controller towards some part, some items of the memory rather than others. So probably the goal, I don't know. I don't know indeed. I don't know. It's like asking the controller. Of course, there are simple ways to do that. Having a goal outside of the system, and when you have extracted trajectories, only select those that fit with the goal. But this is, very would not be interesting indeed. One interesting approach could be to have the goal, as an input to the controller. I don't know. I don't know. Don't seems to be easy, and I should have time to reason on that.
Okay, thanks. Any other question? You can ever put that on chat or raise your hand.
We have been perfectly in time. It's,
yes, very good.
6 and 2.
Yes. Okay. So if we don't, you again have the.
Anyway, feel free to send me messages or information requests that you like.
Exactly. So
I will send to Mohammed Chetwani an updated version of the slides that I modified just a few minutes ago.
Thanks, Alberto. Thanks for all of you to attend. So please follow also the stuff on the AIDA website. You will have the video and also the presentation and the following presentations and lectures from researchers and professors. Thank you again. Thank you, Alberto, for this very nice talk.
Thank you all. Thank you for your attention. Thank you.
Bye.
Ciao.